All right, so now we are moving on in our lectures to think about programming neural networks. As you can see, I've now done away with the suit, and I am in basically an engineer, software engineer's outfit. Hoodie, shirt, jeans. So now we can actually build a neural network and make it legitimate because I've got the right look for it. All right, here's a neural network. And I want to just show you this as a generic architecture, and part of our goal right now is to start to understand what neural networks, what deep learning, what these things entail, and how do they work. Okay? So I give you a generic representation of a neural network here, which basically has some prototype structures that we're going to play with, that we're going to program, and make some magic happen in terms of the kind of things we want to do. Okay? Which is maybe do regression and classification of data sets. So neural networks by design are a supervised algorithm, a training algorithm where we have provided for it labeled data sets. Okay? So your labeled data comes into the input layer, and it goes through the network to an output layer. So there's an input and an output, and for instance, when we use this for doing classification, the idea is you put in an input data set and it gets labeled at the output. So for instance, the label on the output could be if any one of these lights up here. So for instance here, if you're trying to classify an image, it might be a dog or a cat or a car. One of these would light up here. Okay? So that's the idea is you give me an image, I go over here and I classify that image in terms of the things that are in that image. That's one possibility of how you might do something with a neural network. We're not going to focus on image processing in this class. Mostly what we're going to do is think about how can I use such a structure to think about dynamical systems. Okay? Now the network itself can have many layers to it. Okay? So for instance here I've shown you two hidden layers, an input and output, the two hidden layers, and some connectivity between them. Okay? The connectivity graph between them, or the weights between nodes, is given from layer 1, from this input layer to layer 1 is A1. That defines all of these weights here. From X1 to X2, we give that as A2, and from X2 to X3, we give it as A3. So these are matrices telling me about the connections between them. In general, the connection between each layer can be through some nonlinear function. Okay, so it's not to represent that it's a matrix multiply, although in one of the simple examples we do, we'll just consider a linear function between them. Okay? So this is the idea. You can have multiple layers this way. The dimension of these layers internally are also flexible. They can be big, they can be small. There's all kinds of possibilities about what you might do. The input layer is typically determined by the type of data you have. So for instance, if I'm looking at image data from a camera, whatever the pixel count is, that's the dimension here. And the type of labels I'm trying to get would determine the number on the output layer. Okay? So these dimensions can vary depending upon the application. The number of layers in between and the dimensions of those can also vary, as well as the functions between them. There is just so much flexibility and so much to be able to program into this architecture to make this thing work, or even to train some data set. Okay, so a lot of design options. So that's a plus for you, but it's also in some sense a negative in the sense that there's going to be a lot of tuning involved to make your network work for a particular type of data set. Okay? So this is a generic architecture. Go from an input, go to output, through some layers, and each layer has some function that takes you from one layer to the other. The dimension of those layers can change, and we'll talk about some of the different network architectures towards the end of these lectures that have been successful in different kinds of applications, but that's the way we want to do this thing. Now, how do we determine what we want to do here? Typically, you would prescribe the functions between layers. You'd prescribe the dimensions and the number of layers. What the neural network training does is you're going to give it some labeled data. This input corresponds to this output. And you may have many, many labeled data sets. And typically that's the thing. If you want to train a neural network, you need a ton of labeled data sets For instance, for images, the transformative aspect of this happened when you went to deep neural nets. In 2012, the ImageNet data set was made available, and it had 15 million, ballpark 15 million, labeled data sets. So that means you knew the input-output relationships of 15 million data sets, or pieces of data. And so what you were to do is to train the weights, A1, A2, A3, or however many different layers you have. Your goal now is to pick those weights so that you can minimize the error in the classification between the input and the output. That's what ImageNet was able to do, and it produced transformative performance gains. Okay? In fact, most of computer vision now, deep neural nets have sort of revolutionized the field, and they have the top performing methods and algorithms out there these days, these deep convolutional neural nets, which we'll talk about a little bit later. Okay? What I want to do is start with something much, much simpler. I would like to start off with a simple network to help us get going so that we can see how all the pieces would fit together. But ultimately, at the end of the day, when we think about setting this structure up, it's going to lead to an optimization problem. In particular, this optimization problem here. What we're going to think about doing is from the input layer to the next layer is through some nonlinear function. That output goes through another nonlinear function, through another nonlinear function, all the way to the output layer. That's the generic structure of this thing. So the output is a composition of all those functions, right? So the information cascades through this network in a compositional framework. So part of the way the optimization is set up is that you're going to optimize some function which is compositional in nature. So F1, the first function taking you from the input to the next layer, we'll call that F1, is parameterized by A1. Those are all the weights, and it takes the input X. But now this becomes the input for the second layer, which is parameterized by A2. Those are the weights, and through some function F2, and then through F3, all the way through F of M. Let's say I have M layers in this thing. So I'm going to walk my data from the input to the output layer through a bunch of functions. And what I'm really trying to do is when I map all those inputs and outputs together with all the data sets, I'm trying to find the values of all these A of J's, in other words, each of these matrices, so that I minimize my classification error. Okay? So for instance, if that's your task is classification, you're going to minimize that. If you're doing a regression task, you're trying to minimize the residual of that regression. So this is a generic structure for what we're going to do. Plus, you add a regularization potentially. So for instance, you could say, I want my matrices to have some sparsity structure, so you might put some L1 penalty on the A's. You might minimize the L2 norm. You might do a ridge or a lasso. These are the kind of things you might put here as a regularization to this optimization problem. The main thing you want to think about here is this is a massive optimization. This is so one way to think about it is just a regression, but the regression, the number of unknowns in that regression can be in the trillions, because now you're going to train, especially if you go towards computer vision tasks, all these layers all connected together produces for you trillions of unknowns. Okay? So the way you typically solve such large optimization problems is through gradient descent. And we're going to talk about gradient descent and a little bit later in lectures about how you would actually formulate a tractable gradient descent. In particular, stochastic gradient descent is sort of a key piece of making neural networks actually computationally tractable. So we'll think about how to do that. And we'll also think about how to even set up the gradient descent algorithm with the network I drew. And that's done through what's called the backpropagation algorithm. And all backpropagation is framing the gradient descent problem you have to solve for this minimization here. Okay, so that's the generic structure. We're going to get into the theory later. What I thought we'd start with, though, is something very simple. The simplest neural network possible in some sense. And so what I want to start thinking about, so here we go. Sorry, I just wrote it down. So there's our objective function. There's our regularization. Those are the things we're going to start looking at. But I want to start off with something much simpler. A one-layer network with an input and an output. And my task here is I'm going to give you images of dogs and cats for the input, and the output is a single number, and if it's a +1, that's ideally what I like it to be. I'd like it to be a dog. If it's a -1, it's a cat. So I'm going to take all this information, project it into what's called the perceptron. So this was the original name of it for the neocognitron in the 1980s. And the idea was let's project onto a single indicator variable. And really this would be the sign of this. So if it's positive, I'll make it a dog. If it's a negative, it's a cat. So if I just take the sign of the thing as +1 or -1, and that became essentially the perceptron. The output layer was a single node, which if it was positive or negative, tells you if it's one thing or another. It's a binary classification, right? So in this case here, we have an input layer just to that single node. And what I'm going to do is make it so simple, because what I want to try to do is just hit it with the matrix A. So I'm going to take the initial input layer, A, it's going to be a linear function mapping over. So A tells me the weights of all of these, and it gets me over to the output node, which I just want to see is that thing positive or negative. Okay, so that is about as simple as it gets. It's linear, there's one output layer, one output, and there's only one layer of this thing. Okay, so I think this is a really nice example because in some sense we can frame it all in terms of normal mathematics, AX equal to B, that we normally do. Okay, and yet it still represents the kind of things philosophically you want to do in neural nets. Okay, so that's my neural net. And that's what I'm going to trade on. Input layer, output layer, and essentially now, this is going to lead us to a linear regression. So in most neural nets, it's a nonlinear regression, but now we're just splitting hairs. It's a regression, whether it's a linear or nonlinear function, we're just optimizing. Okay? And so how do we frame this? Well, for this specific example here, with this input layer to one output, here's how I'm going to frame this linear regression. It's AX equal to Y. And here's how I'm going to say it. A are the weights, okay? So A1, A2, these are the weights that go from the input layer down to that output. Now the X are in fact my input data. So these are X1, X2, all the way through XP. So I have XP different inputs. These are cat and dog pictures. This is what we're going to assume for right now, is that we have cats and dogs. And for instance, in the example I'm going to show you here, we're going to go ahead, line up our dogs, line up our cats. And so the first N of these columns will be dogs, second N will be cats. And each has a label, +1, and then when I get to cats, it's -1. So that's it. This matrix here, which is a vector in this case, times my data has to produce 1s or -1s, or at least that's what I'd like it to do. Okay? So I'm going to give you all this data, and your job is to then figure out a solution to this AX equal to B problem. That's all it is. So now it's linear regression. You can just do backslash, for instance. But you can also do other things. You can do the lasso. It's just AX equal to B at this point. And there are many ways to solve AX equal to B, and at least this linear regression, it shows us already. If I do backslash, it's doing some kind of least square fitting of these coefficients that best matches the inputs to outputs of the data. Okay? So that's the simple setup of this thing. And, here's a simple solution. A is equal to, just take the pseudo-inverse on the right side of X, then X pseudo-inverse is identity, X, Y pseudo-inverse, and here is a least squares solution to this thing. Okay, so I could use the PM command to get this. PM will do least square fitting. There's your least square solution. Okay, so far I've cast this neural network, this very simple one. If it's a linear function between these two layers, is just simply a least square fit, which is something we're very familiar with. But it is a neural network. If I had a nonlinear function between them, I couldn't just do a backslash. I would actually have to solve some nonlinear optimization problem. And we will actually train to do that as well in a later lecture. So that's the main thing. That's all it. That's all this is. So what I want to do is run through some code. And with this code, I want to show you what this looks like. Okay, I'm back. All right, so I had to load some data on here. So here's some code. You can find it on the website for the course. What I'm going to do is I'm going to take some data of dogs and cats, In particular, what I have here is load cat data underscore W. So what these are cat and dog pictures that have actually wavelet transformed them first. And what wavelets do is they tend to highlight the edges. So I'm not so interested in the coloring and the shading of the dogs or cats. I just want to kind of look at the basic structure, and this wavelet decomposed dogs and cats is a little bit better to look at in terms of doing classification and also picking features out for the neural network to train with. So I have cat data, I have dog data. So I pulled these both in, and then what I do is I make a joint right here. Sorry. Let me go over here. I also make this thing called CD, cat dog. This is a matrix with the first 80 of these are dog, first 80 columns, the next 80 are cats. Okay, so I just stack all the data. So what I have left over here is each image is 32 by 32, so it's 32 squared rows and 160 columns. The first 80 are dogs, second 80 are cats. And of course I have labels for all these, right? So the dogs are going to be +1, the cats will be -1. So CD has my master of information. Okay? Now what I'm going to do with this is I'm going to go ahead and pull apart the data. I'm going to call this here the training set and the test set. So I'm going to take the first 60 dogs and the first 60 cats and make a training set. Okay, so I pull out the dogs, pull out the cats. I have a total of 80. And I pull out the remaining 20 of each to make a test set. So what I'm going to do is train this neural network on 60 dogs and cats, and to see how well I do, I'll train it on the remaining 20. Normally what you'd want to do is randomly select 60, randomly select another dog, 60 cats, and then so that way your test set is a random selection. We're not going to get into that right now. That would be an important piece to do for cross-validation. But right now I just want to show you the basic structure of what we want to do. So training set, test set, and here are my labels. What I'm going to do is now make a label vector. The labels are 1s for the first 60, -1s for the next 60. So corresponding to this matrix train, which is 120 columns total, the first 60 columns are dogs, the next 60 columns are cats, 32 squared rows for the picture size, is a label -1 and 1. Okay? This is what I got here. What I had just showed you previously was I have the y and the x. The x vector is this train, the y vector is this label, and so now I can just solve this thing. And what I'm trying to solve for are the weights that take me from the input space of the image to the label space, ±1, of my data set, which is the categorical decision about what they are. Okay? Simplest thing to do, Suta Members. I just showed you this a few minutes ago in the backup there. I just said, okay, generically you're going to say, take your labels, which is the y vector I'd shown you previously, times the pseudo-inverse of train. So this is the y pseudo-inverse of x that I'd showed you before. So that's going to give you A. It's the least square fit to the matrix A, taking you from the input space of dogs and cat images to the output space of a label of ±1. Okay? And then the label, so now what I do, once I have A, I can actually find out how did A do on the test set. Right? I've trained this thing on a set of data. I want to go look at how well does it label the test set, which was never part of that training. So all I do is I take A times test. So it's going to take A times my images. It's going to project it down to hopefully something like a ±1. And all I care about is the sign of it. So is it positive or negative? Those that are positive will be considered dogs. Those that are negative will be considered cats. That's it. AX equal to B. Solve a pseudo-inverse. Okay? I'm going to plot the results of this. So when I plot here, this is a bar plot of those test labels. I'm going to see if they're plus or minus 1s. The first 20 should be +1, the next 20 should be -1, and you'll see it doesn't get them right. all of them right. I mean, get you some, many of them right, but you'll get some of them wrong. So I'm going to show you that. I'm also going to show you here a subplot of the distribution of the A values. So the A itself now is this matrix taking from one to the other. So what we're going to go look at what does the A matrix look like. Okay? Then what we'll do is that's the main thing we'll do, and then we're also going to plot what the A matrix looks like. That's what we're going to do here in this second figure. Now we're going to do that, but we're also going to, instead of just doing the backslash, remember the regularization in these neural nets makes a big difference. Anytime you do optimization, you're going to try to find a function, and your goal is to find that function, but also to potentially apply some regularization to give you a better control of the kind of output you have. So here what we're going to do is solve for that A, promoting sparsity. In other words, we're going to say A, take the lasso, the training, this is your X, your Y, and then the lambda value is 0.1. And of course you can play around with that, make it more or less sparse. So this is another way to solve AX equal to B. It's a different regularization. Remember, when we do pseudo-inverse, the regularization is least square fit, so the L2 norm is minimized. Here, the L1 norm is minimized. And we're going to plot the same kind of diagnostics that we did previously. So what I want to do is run this and start to diagnose how we did on this very simple model architecture, which is just AX equal to B. Okay, so let's run it. And we'll start off here, figure 1, on our diagnostics. So what you're looking at here on the top and the bottom is your least square fit and your L1 lasso fit. So when you build this matrix A from regression, it is now the matrix that you can take and hit it on the test data to see how well you did. So what you see here is when I hit this new test set, the first 20 are supposed to be all +1s. And you can see I got many of them to be +1, but I got 5 wrong. 5 out of the 20. Okay? So the idea is I get about 75% accurate in terms of this withhold set that I had. Whereas with the cats, notice what I have here, I've got 3 wrong. Okay? 3 out of the 20. So I did much better with cats than dogs. Right? So I don't get a perfect, even when I do this regression with the training, I don't get a perfect classifier, but I do something that performs reasonably well, especially given the limited information I give it. What this shows you is the values of the A matrix. So right, all of them are non-zero, which would make sense because I did a pseudo-inverse. So least square regression tries to make everybody small across the board and to give me the best fit. Okay? So that's what the A matrix looks like. In contrast, if I do the lasso regression, here's my performance. So my performance, notice for the dogs, I get quite a few dogs wrong under this lasso regression. And of course, I'd have to play with that lambda parameter to see how well I did. And typically, you might tune that lambda parameter that promotes sparsity, you might tune it with doing cross-validation. So you might get much better performance if you get a better sparsity pattern. Whereas with the cats, I only get 2 cats wrong. So again, cats in general seem to be easier to classify. In fact, they are, because they have very nice ear structures to them. But the dogs themselves are much more difficult. But again, you can see there's a very different strategy here for giving you the classification. Because now if we look at the matrix A, here's the matrix A here. And what you see here, these are the non-zero components. So there's not very many that are non-zero, which of course is what we expected because that's what it was doing, promoting sparsity. In fact, we can go back and look at the matrix A and look to see, if we look at that matrix A, what does it look like? Does it have some kind of interpretability for this linear map from the input to the output space? And in fact, it does. And remarkably, it gives you some very nice information. And here it is. When I do the least square regression, so that all of the pixels matter, this is the weighting of the pixels. This is the matrix A in the P color. And notice what it looks like. You can see sort of a cat-like face in there. You got eyes here, a nose here, triangular ears for the cats. In fact, if you look at the data set, it clearly is inheriting the structure of your cat-dog data set. In particular, the cat has these very strong features around the ears. And partly that's why also classification with the cats is much easier than dogs. So again, this A matrix is interpretable. How you go from one layer to the next through this map tells you where most of the measurement is happening about making a decision for classification. In particular, it's saying, I'm going to make my decision about whether it's a cat or dog based upon these dark spots, which are the eyes, nose, and ear features, which is exactly what we would do, actually. Okay? If you do the lasso regression, now it's penalizing things that it wants to keep things sparse, turn most of the things to 0, and it says, I'm going to make a decision, at least for lambdas 0.1, based upon these pixels here. Look where they're located. Eyes, ears, same kind of thing. The lasso was also keying in on key features of faces. Eyes, ears. This one doesn't even have any nose information. But again, depending upon how I switch the sparsity up, I can bring more pixels in to help make a decision and maybe even make a much more accurate decision. So this gives you a very simple example of how this works, right? It's an input layer to an output. All I did is regression. The only thing that's going to change in more sophisticated neural network architectures is I might have more layers and they're going to be nonlinear. Okay? So I can't just do backslash or lasso. Now I actually have to solve some nonlinear optimization problem that is high dimensional. And that's where we're going to have to use something like gradient descent. And that's going to be very expensive, but we're going to talk about how you can actually make that computationally feasible and how you speed up that computation. But in either case, this exemplifies all the key things you want to think about. There's an optimization step. There's a map from input to output through some network architecture where you have to determine all the coefficients in some optimal way. Okay, so that's part one of what I wanted to talk about here. Next, I'm going to give you an example of this for dynamical systems.